Calculus students, this is our last section of Chapter 1, Mathematical Modeling Variation. We're going to be focusing in on the variation and look at all four of these different types. There's a lot of the rest of the chapter is on statistical modeling, which you'll do more if you take AP Stats, and you'll do in the future. First of all, direct variation. All these statements are equivalent. Y varies directly as x, y is directly proportional to x, y equals some constant times x, and that k is the constant variation, also called the constant of proportionality, because you can set up a proportion with these. If y varies directly as x, then y1 is to x1 as y2 is to x2. So that we can add to there too, that you can set up a proportion when it's directly proportional to. Now, let's look at this example. Junior's cruising at a constant speed of 10 miles per hour. Write an equation for his distance as a function of time. So, is it directly proportional? Well, from your studies, you remember distance equals rate times time. And now the rate is constant. So, distance equals 10 miles per hour times time. So, you can see when we put in times, in hours, we'll get miles for distance. Let's make a little chart. Time and distance. If Junior bikes for 2 hours, he's going to go 20 miles. If he bikes for 5 hours, he's going to go 50 miles. And this is what I was talking about over here, that we can set up this proportionality. That is, distance 1 is to time 1, as distance 2 is to time 2. So in this example, 20 miles is to 2 hours, as 50 miles is to 5 hours. Notice how they both work out to be basically 10 miles per hour. That's our constant proportionality. That's an example of direct variation. Inverse variation, or here, direct variation as an nth power. Y varies directly as the nth power of x, or directly proportional to the nth power of x. This is where you just put a power on n. I picked this up from Wikipedia. The third law of Kepler. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. So that's basically the average distance away from the sun there. So the square of the orbital period is proportional to, so equals some constant of proportionality times the cube of its orbit. Now we can get this as one power by just saying P equals K a cubed and raise each side of the 1/2. So now we can look at it as one power on P. So P equals, we can call it some new constant, Q times a to the 3/2. I could write K to the 1/2 square root of K, but I can just use a new constant here. And you get this idea that P equals some constant times a to the 3/2. The period is directly proportional to the 3/2 power of the orbit. Now let's actually come up with an equation from some data I got off of Wikipedia as well. And let's conveniently use Earth and astronomical units. So we're going to have the period in years. So this is P here. And the mean distance from the sun, A, in astronomical units, AUs, which is basically the distance from the Earth to the sun. And notice how both those are the same. So P equals Q times a to the 3/2. We're going to have P for the Earth is 1 year equals Q times A, which is 1 astronomical unit, raised to the 3/2. And anything to the 3/2 is 1. But what you see here, we get for our formula then for Q, we get basically 1, but it's astronomical units to the 3/2 power over years. So strange units on it. And basically our formula just then becomes then the period equals 1 astronomical units cubed, or to the 3/2 over a year. That's our constant of proportionality times the mean distance to the sun to the 3/2. So let's see if this works now, this little formula we came up with from some of the other data I got on the other planets, which I think is up in here. Yeah, let's put in we've got the distance from the sun for Neptune here is 30 astronomical units. So if we put for Neptune, well, Neptune's 30 times as far away from the sun as we are. A equals 30. So now you can put this in your calculator, basically 1 times 30 raised to the 3 divided by 2. Let's see what we get. And we get the period equals 164.317 years. Let's see how that compares with the actual facts here. Scooch on up here. Neptune, there it is, 164.79 years. We're a little off, but that's probably because we did some rounding on Earth and so forth. Terrific. Okay, next step is, this is just checking some other stuff I got from Wikipedia. There's using that proportional symbol, that alpha to represent P is proportional, P squared is proportional A cubed. They came up with a proportionally constant. It looks a little different than ours because they went with that. Notice they've got a number very close to, see, they changed it from astronomical units to meters, and that's where they're getting all these numbers from. Okay? And here's another one for general primary bodies, that is if you want to do something other than the sun. So all sorts of extra info I got there from Wikipedia. Let's do a little example of inverse variation. The following statements are equivalent. Y varies inversely as x, y is inversely proportional to x, y equals k over x. So one of the key ideas here is that as x increases, then y decreases, which we did not get in the other example. As x increased, y would increase. So, and when you look at it graphically, it generally looks like a hyperbola like that. It's decreasing like that. And we usually focus just on the first quadrant. I know there's stuff going on over here in the third quadrant, but here's your idea behind x is y. As x goes up, y goes down. As y gets smaller, as x gets smaller, y gets bigger. So here you're told that in Boyle's law, the product of the ideal gas pressure is always constant, and volume is always constant. PV equals K1. So we can change this to say P equals K1 divided by V. And now it looks like our idea of inverse proportionality. So what happens if volume is doubled? If volume is doubled, what happens to pressure? What happens to pressure? If volume is doubled, what happens to pressure? It's a different kind of problem where you're not actually given numbers and figuring out the constant. You're just given sort of a change. Well, clearly the volume is going up, so the pressure is going to go down. But by how much? Well, we can express that by saying a couple ways. The volume is being doubled, so what's the new pressure? We can say PV equals K1. And so P1 V1 equals P2 V2. And now let's say this is our original pressure and volume. Find P2 if V2 equals twice V1. Okay, P1 V1 equals P2 times, replace V2 with twice V1. So the V1's cancel. P1 equals P2 times 2. Or P2 equals P1 over 2. The pressure is cut in half. The pressure is cut in half if you double the volume. Okay? All right. Joint variation is when you have several ideas going on at once. Maybe it's not just one variable in terms of many others. So we say that Jerry varies jointly as x and y basically implies that we're multiplying them. And C is jointly proportional to basically the product of x and y. So I dug this up from my old naval training days, and I was surprised to see that, wow, this is not classified. Time, distance, and shielding were 3 ideas of protecting yourself from radiation in a nuclear power plant. So let's just try and come up with the idea behind how do we, if we let t equal time and d equal distance, and we'll talk more about shielding in a second. But if you want to come up with an equation based on those two, we have that your exposure, your radiation exposure, it says in here, reducing the time reduces the effective dose proportionally. So that implies a direct proportion. So we're going to be directly proportional to time, so K times T. But increasing distance reduces the dose due by the inverse square law. So it's inversely proportional to the square of the distance. So there you go. Now shielding, we'll have to learn more about exponential decreases and so forth, that we can incorporate shielding in this. But for, I can just, now let's do a little bit of extra work with actually turning some of these things into equations. Find the mathematical model for a verbal statement. I made a bunch so that we could always come back to these later. Let's look at h here, varies directly as the square root of s. So that means h equals k times the square root of s, and so on. That's it. Just translating in there. Well, v varies directly as the cube of e. v equals k times e cubed. Now, you can be expected to actually do a little more, though, in terms of setting up equations given specific information. Let's look at this one on 76 here. V varies jointly as P and Q and inversely as the square of S. Oh boy. V equals K times P times Q, and inversely, so this is going to go in the denominator, the square of S, S squared. So now it gives you all this extra information. We can use this to figure out what K is. I might actually solve this algebraically first and just say, let's multiply both sides by S squared. And then K then equals VS squared over PQ. And now let's sub in all those values. I subbed everything in. 1.5 in for V, 1.2 in for S, 4.1 for P, 6.3 in for Q. And I got this constant. So to make the whole equation, we'll write it as V equals the constant, 0.083624 times P times Q all over S squared. So that's called the equation with the evaluated constant. Okay? All right, one last example. And that's, here we go. If P varies directly as Q and P equals 5 and Q equals 3, find P when Q equals 6. Now, you don't have to actually find the constant proportionality. You can write to saying P1 is to P2 as Q1 is to Q2. And we can call this P1, and this P2 is unknown, this is Q1, and this Q2 is known. Now, things you might say, well, that's not how you said it before. Well, as long as you're consistent with letters and subscripts, you can set the proportionality. So actually, I want to find P2, so let's set it up another way. P2 is to Q2 as what? Well, P1 is to Q1. That's legal. So P2 over Q2, which is what we know, 6. P1 is 5, and Q1 is 3. So there we go. P2 equals 6 times 5 over 3, 33rds, or 10. Now, this is pretty much the same example, but I changed the word to inversely. It's now with inverse variation, it's P1 times Q1 equals P2 times Q2. So if we call this 1, in this case 2, we get P1 5 times Q1, which is 3, equals P2, which is unknown, times Q2, which is 6. So we get 15 equals 6P2, or P2 equals 15 sixths, which reduces down to, take out the 3's, 5 halves. There you go. Flange out.